No. And to this the Thursday's spin-off that they are under the auspices of the SAMCA, Cátedra SAMCA of Nanotecnología of the University of Zaragoza. And today is with us David Fairen Jimenez from a company, from IMMATERIAL. It's a company, he will explain us better the reason why he's here. Well, he's here, virtually here. And I will just introduce you, David. David is co-founder of IMMATERIAL. I have some notes here. IMMATERIAL and chief scientific officer of the same company, and he leads the research and technology areas of this company. He is also a research fellow, University Research Fellow for the Royal Society, and also belongs to the Department of Chemical Engineering at the University of Cambridge, where he is a reader in molecular engineering. Also, he has a group in the University of Cambridge, the Absorption of Advanced Material Laboratory in the same department, the Department of Chemical Engineering, and his research is focused in application of molecular organic frameworks, so-called MOFs, in energy and nanoscale drug delivery. Okay, he is here today, as I mentioned, to give us a presentation entitled IMMATERIAL, Material Design, Material Discovery, and Molecular Engineering of MOFs. So, David, the floor is virtually yours. So,
okay, thank you very much. So, thank you very much for the kind introduction. Okay, you should be able to see the slides now, right? And you can see my cursor as well, right?
Yes, we can see. But...
Can you see the red laser as well?
I think you have to share your screen, or just a minute. Maybe we can just take this out. Okay. No, it was okay. It was okay.
No. I'll say this again. And can you see the red cursor? Okay.
Now it's okay.
Okay. And you can see the red thing. Yeah. Okay. I can see this in the screen. Perfect. So, well, thank you very much for the introduction. And as you have said, I'm going to talk about what we are doing in IMMATERIAL. And before I really start with the slides, basically, I mean, I would like to say, I joined the University of Cambridge in 2013. IMMATERIAL started from an invention from the first PhD student I had in my group. So what I think is quite interesting was he was working on a project. It was not related with what IMMATERIAL is doing. He was working on a drug delivery project, and one day he had a problem because he didn't have enough time to finish an experiment, so he forgot a sample. And instead of putting this sample inside the oven to dry the material, he was working with a metal organic framework. He forgot the sample on top of his bench, and then the day after, when he came to the lab, he found an interesting material, which is these monolithic structures that you can see at the bottom, I mean, on this slide. And instead of throwing away the sample, because assuming something, well, he forgot the sample, and obviously it's not what he was looking after, he continued looking at the material, trying to understand what was happening and trying to see if it was important or not. So he came to my office and he knocked at the door and said, I found this material. And as soon as I saw the morphology of the structure, I saw the material was transparent. It wasn't the one we have here in this slide, but it's one that I will show later. I was able to know that the material was going to be highly dense, very well packed, which was a big challenge that we knew we had with metal organic frameworks. And at this point, he changed completely the topic of his PhD, okay, because he found this after the first year. And he started focusing on this, basically what we call monolithic metal-organic frameworks. Okay, that's just the starting of the company. We really started in 2015. We spun out from the University of Cambridge in 2015, and now we have a team of about 20 people working directly in IMMATERIAL, plus the board members, advisors. We have about 10 extra people. So we have about 30 people, a team with really, really important advisors with a lot of knowledge about what are the main markets and areas where we can really apply these structures. So what I'm going to show is a little bit what is the fundamental knowledge that we have in the company, which is basically coming also from the research we do at the University of Cambridge. So hence the title about material discovery, okay, material discovery and molecular engineering of these metal-organic frameworks. Just to start with, basically, this is a slide. It's a little bit of explaining the motivation behind the research that we are doing and the work that we do in the company, right? This is the projections of population growth, and this is billions of people. And this is the year where we have highlighted here 2 important dates, okay? That's the end of the Second World War. And at this point, you can see there was a huge increment in the population growth, okay? From this black estimation, that was an estimation, into this more detailed information. This is where we are now. And I have included here 3 different predictions. The most realistic one is this orange one, okay? This suggests that by the end of this century, we will end up with having 10 billion of people living on the Earth. And obviously, this is because we have great advances as a society, but we also need to recognize that we are going to face very important challenges, okay? The exploitation of natural resources, water, drinking water, healthcare applications, food demand, pollution, energy, and so on. IMMATERIAL try to find solutions for most of these problems, okay? That's also a different way of introducing these problems we try to attack. These are the 21st century global challenges. And if I want to highlight just a few ones that are extremely related to what IMMATERIAL is doing, it could be related with drug delivery, hydrogen storage, carbon capture, methane absorption, global warming, okay, and so on. So really, really important applications for the society, all in all. Something very important is that we are a chemical engineering, chemistry company. And one of the main ideas we try to focus is related with the fossil fuels. Okay, we all recognize that fossil fuels are causing big problems, obviously, on the global warming, okay, and climate change. And it is also important to recognize how critical these materials were in the past. In the 18th century, we started working with a solid that was coal. That was the start of the Industrial Revolution. We needed to have access to a very cheap way of getting energy. Okay, so 18th century. In the 19th century, people started moving into a liquid from the solid. Okay, the use of petroleum, not only for vehicles, but also for a lot of different processes in industry. From the solid to the liquid, in the 20th century, we started working with natural gas as a greener energy than coal in particular. And now we are always talking about the future economy of hydrogen, especially when we are using green hydrogen, okay, or at least blue hydrogen. So green hydrogen is the one that is coming from renewable energies, and blue hydrogen is the one that is coming from fossil fuels, but we have also carbon capture incorporated into the process. And obviously, the challenges that are associated with a solid, a liquid, and a gas are going to be very different, okay? Solids are very easy to handle, liquids as well. Gases is a different issue because the concentration, I mean, the density of these gases is always going to be very low. And this is why we highlight, I mean, that's an alternative name for this presentation, right? Porous materials and the age of gas. And this is something that was highlighted by Professor Susumu Kitagawa 6 years ago. How porous materials could help to handle all these gases that we have, so we can really move into this future hydrogen economy. And from these 30 chemical engineering processes, okay, that we have in industry, we also want to highlight the importance of these new chemical engineering and new materials that we have. Okay, this is where we try to combine advances in nanotechnology, advances in green chemistry, also with computational techniques, machine learning. Okay, finally getting new materials that will solve all the problems that we have in industry, okay? And in particular, everything related with this pollution of the atmosphere, and basically how to have something which is based more on renewable energies. And at least if we are still working with fossil fuels, so we can really work on carbon capture applications. So within material, we really focus on metal organic frameworks, right? These are one of the most important developments of this century, okay? They were really created, we can say, in the 90s, beginning of the 90s or the end of the 90s, depending on the definition of what is a MOF or not. But these are really beautiful structures that can really be used in multiple applications, okay? But within material, we try to focus not only on MOFs, we also have a lot of different materials. We also focus on zeolites, for example, where we really try to find new opportunities for all these different structures, okay? And the whole idea that we have is that we want to understand the physical chemistry that is involved in all the absorption phenomena, so we can apply all this fundamental knowledge into specific industrial applications that we have, okay? We have some processes where zeolites work extremely well, but there are other applications where there is still no solution, okay? And do we want to have cheap carbon capture? Do we want storage of hydrogen? Activated carbon, zeolites, these are great materials, but many times are not enough. We want to work with these MOFs. Anyway, IMMATERIAL is basically based on three main pillars, okay? One is related to the modeling capabilities that we have been able to develop, okay? Everything developed in the university and the academic group, and basically extrapolated, spin out into IMMATERIAL. We do classical simulation, Monte Carlo, molecular dynamics, but we also work with process modeling and machine learning capabilities, okay? This basically allows us to screen thousands of materials that exist in the literature to be able to find what is the best structure and what structure will solve a specific problem that we are trying to solve. Once we have been able to identify the best material, okay, then we move into this, the connection with the material discovery. We do the synthesis of this structure and we do the shaping of these metal organic frameworks. And this is a core IP that we have been able to develop in the last 5 or 6 years. Then we move into the whole engineering domain, okay, going back to these modeling capabilities where we try to do this engineering possibilities where we scale up the synthesis of the materials, of course, but we also work on process optimization. We want to not only to manufacture a structure, okay, we want to create solutions for specific problems. And with this, we work very closely with clients that are interested in the MOFs, but not just in acquiring the material, but also in developing the whole system, okay? We work with them to develop systems that will be useful. So I guess everybody will know in a course in nanotechnology what is a MOF. Just in case, this is a very generic slide that I use to explain what is a metal organic framework, okay? The definition is never clear, but everybody knows what is a MOF and what is not. We can basically say that a MOF is a porous coordination polymer, okay, which is created by the self-assembly of these red spheres that you can see here in the slide, linked together by these organic molecules that you can see as blue units, okay? We have all these different building blocks. We put them all together and we create these beautiful structures that you can see here on the right. This is just a cartoon, okay? This will continue growing in 3 directions. We have 3-dimensional materials. Sometimes we can also say we have 2-dimensional networks and so on, okay? But basically, what is important is that we will be able to exploit all the porous space that we have created between the building blocks, okay? And we are talking about materials which are extremely porous. We are talking about materials with extremely high pore volumes and potentially extremely high surface areas, okay? Sometimes we have seen materials in the literature with up to 8,000 square meters per gram, okay? That's a dream for people working with porous materials. But these materials are not perfect, okay? And in material, we want to recognize what are the opportunities and what are the big challenges that we need to solve. One of the big problems is that when we have a material with 8,000 square meters per gram, okay, this open structure will suffer a lot. It will have low mechanical stability and will have very low thermochemical stability, okay? Sometimes just in the presence of water, these materials decompose. So obviously, it's not the end of the world. We want to focus on materials that will be stable in the conditions we really need to use, okay? So it's a challenge, but we have solutions for that. We can play with the pore size of the structures, okay? You see, this is an organic molecule. We can have something which is shorter or longer or with a different geometry, and we can really extend the size of the porosity that we are having here on the right, okay? At the same time, again, talking about materials with 8,000 square meters per gram, we are going to have materials with very low density, okay? And this is a critical problem that we will go back later on when we really go into the engineering of the systems and the monolithic structures, okay? We want to have a material at the end of the day, or most of the times, with very high surface area and very high pore volume, but at the same time, we want to have a material with high density, okay? And this is a balance that we just need to understand and we need to solve. And again, this is where we are trying to apply all the knowledge we have, okay? Thousands of materials. There are 100,000 different metal organic frameworks. We can find them for almost any application we want, okay? We want hydrogen storage, carbon capture, separation of gases. There is a material out there that will be able to work extremely well for these applications. But there is a problem as well. If we have 100,000 materials, how are we to find which one is optimal, okay? Which one is the best one? We don't know. But these materials are crystalline. We know the position of the atoms, okay, from the structure, and this is something we are going to exploit. So one of the big questions that we have had, it's a fundamental philosophical question in immaterial, is can we find a deterministic prediction for materials performance? Okay, trying to answer this question is quite important for us. Can we use any computational method that will allow us to have a deterministic prediction, right? And also, the second question is, okay, we have found the best material. Can we really translate all these predictions that in principle we aim to have into real materials and applications at a scale? And at a scale means ton scale, okay? Or are we going to just have something really beautiful in the computer, but as soon as we try to manufacture these structures on ton scale, we will fail completely. Going back to the MOFs, something important, okay? We are talking about materials with extremely high surface area. What is high? A zeolite, you can have good zeolites with up to 600 square meters per gram. With activated carbons, you can really go up to 3,000 square meters per gram, okay? Extremely high. With MOFs, this is what I'm talking about. Sometimes you will be able to reach 8,000, almost 8,000 square meters per gram, okay? Now, remember, high surface area doesn't mean it's going to be good, because this material also probably is going to have a very low density, okay? The same with an activated carbon. An activated carbon with 3,000 square meters per gram will have very low density, and many times these materials are not going to be optimal for some industrial applications. Maybe for 3 of them, but not for all, okay? Important, how these materials look under the microscope. This is a beautiful SEM image of a material called C8. And this is the first material that we develop as a monolithic structure, which is something I want to insist. You can see the beautiful crystallites. These are micron-sized crystallites, okay? All with the same topology, all the same morphology, beautiful structure, highly crystalline material. And the basic idea is that we want to separate or concentrate gas molecules inside the porosity, okay? If we are thinking about a single component, we will be able to concentrate, let's say, hydrogen, or if we are talking about carbon capture, we will be able to localize all the CO2 molecules inside the porosity, whereas the nitrogen and any other gas molecules will flow around. Thinking about gas storage, okay, we can really think about natural gas storage, okay, compressed natural gas versus a MOF tank, okay? And this is important when we talk about microporous materials, porous materials in general. If we take a tank, a bottle, okay, we fill this at high pressure, we will be able to increase the amount of natural gas, okay, methane that we can really put inside. That's a typical cylinder we can really buy, okay? Everybody has, well, in the old times, people had a lot of butane at home, still people have butane at home, and then we have natural gas, not at high pressure at home, but you can really get in a lab a cylinder filled with natural gas, right? You can really put a lot of natural gas inside. Now, what you can also do is you take the same tank, you fill it with a porous material, okay? And the question is, can we have the same amount of fuel, the same amount of natural gas? And the answer is yes. You can really have exactly the same amount of gas. With the compressed natural gas, you will need to go to very high pressure. But with a MOF filled with porous materials, you just need to have a fraction of the original pressure, okay? You can really go up to 50 bar, and that's going to be exactly the same amount of fuel. So this is going to be lighter because you can see also of this cylinder, that's going to be thinner than this one, okay? Just because this tank needs to resist this extremely high pressure, okay? It's going to be safer as well, just being able to have less pressure. This is for natural gas. For hydrogen will be exactly the same, okay? Instead of having 900 bar, we can really work ideally at 20 or 100 bar, okay? A fraction of the original pressure. So this is basically what we want to have. And now what you can see here at the bottom, this is the first monolithic extractor that we obtain, okay? That's something called C8. And this is the material that I said the student was coming to my office and knocking at the door and saying, hey, I have this beautiful glassy look material, okay? It was fully crystalline when we studied that, and then we also observed that it was fully porous, and therefore it was high surface area and high density, okay? Just because the material is transparent. That was a big thing for us. We are exploiting a lot of different applications with these materials, okay? We go for gas separation, we go for gas storage, sensing, energy production, and catalysis, okay? A lot of different opportunities with all these different monolithic metal organic frameworks. So now, just looking a little bit at the literature, okay? And I'm referring to this paper that Professor Gutke from the Basque Country was publishing this summer. You can really see an evolution of the MOF commercialization in the last years, okay? MOFs were reported, I mean, the name was coined by Professor Yagi in 1999, okay? Although people were talking about these materials at least 10 years before him, okay? He was at least together with, I mean, he was creating MOF5 in 1999. There was another paper in Science for HCUS1 that was also basically the first metal organic framework with porosity measure. So few people created this material, let's say about 20 years ago, okay? Or 10, 20, 25 or 30 years ago. In these last years, we have seen rise of up to 27 spin-out companies, okay? Spin-out companies, but also other companies that are related or trying to exploit these metal organic frameworks, okay? It's a jump from the academic literature into different industrial applications. The first one is coming from 2010, okay? The first MOF synthesis at the scale. That was basically one-scale production of these materials led by BASF. And there was the first commercial product in 2016. And this is basically where we are now, okay? IMMATERIAL was created in 2015. The first material to be synthesized at the scale, as I said, was from BASF, okay? They created this in 2010, and the first vehicle made with natural gas, that was in 2014, okay? BASF was the first company that jumped really, really quickly into the more efficient gas storage because they really like the amazing porosity of these materials. There was a problem as well, okay? They were the first ones and they failed a lot. They were hiring up to 30 people in a team working with metal organic frameworks. And they found later on that the materials that they were working, okay, this is from the brochure you can really find at BASF, they are still highlighting MOF5, which is a material that was not stable. So they had a lot of problems, okay? There was a lot of hype on these materials, and this really decreased the attention quite a lot when they observed it was not working. 2016, I said, was the first commercial product. That was a material that was releasing this molecule that you can see here on the slide. And this is a molecule that will compete with ethylene and basically will block ripening of the fruit, okay? So this is very important for fruit transport. Especially if we live in the UK, okay, we don't grow most of the food we need to eat, and basically this needs to come from Spain, for example, and we need to protect the fruit on the process, okay, on all the travel. What material are they using? Well, MOF Technologies is a company from Belfast. They were developing this material, and we don't know exactly what is the MOF, okay? It could be aluminum fumarate as a good material, but this is just an assumption, okay? We don't really know what structure they are working with. The second big product that was created is Ionx. This is from a company from Northwestern University, NUMAT, spin out from Northwestern University. And this was using the materials to, the MOF, to store gases that are used in electronic industry, okay? Really, really toxic gases, okay? Like arsenic, phosphine, boron trifluoride, acidic, basically quite toxic, okay? They store this at 700 torr. And this is good because if there is a problem, if there is an accident, these gases will not be released from the material, okay? They also have some problems because these gases start reacting with the MOF when they wait about 6 months or so, okay? And this could be a problem as well. And now we can also see clinical trials, MOFs used for water harvesting, few groups working on this. This is the first clinical trial that is still, is working now. Okay, it started about 3 years ago, and I haven't seen the results of this, but it's really interesting. This is for drug delivery applications, okay, from Professor Wenbin Lin in Chicago. And the most interesting one as well, I think, is that one developed by Svante. They started last year, and is basically using a MOF called CALF20, and they are basically using flue gas from a cement plant, okay? It's a real gas with CO2, nitrogen, moisture, particulates. They have some discs that are rotating and they basically scrub the CO2, okay? They have free nitrogen here, clean nitrogen, they retain the CO2 here, and then they have steam and they recover the CO2 over here, okay? Really interesting because this is working now at a scale. This is something that is going to be a big market on carbon capture. And we're looking at the how materials are translated to industry, okay, from this industrial perspective. It is important to recognize the importance of these small volume, high value applications, okay, the ones described here by Ionx, for example, or TruePic, these ones that I have highlighted here. But at some point, we really want to move into what we call these holy grail applications, which is these applications where the margins will not be that high as here, okay? We need to have very cheap materials, but we will be able to produce on scale metal organic frameworks, okay? And then it's going to be quite valuable. Many times, we also focus on MOFs with very narrow porosity, okay? And something that is important is that these materials must be easy to synthesize, inexpensive, and chemically stable. The application from Svante is a price, I mean, the synthesis, I believe, is coming from BASF, a price of close to $20 per kilogram of material, okay? So this is how important the price of this material is. Now, really working in IMMATERIAL, right? When I said we like to have all these computational screenings to be able to find materials, right? One of the questions is what is a MOF and how many MOFs exist? This is highlighting, this graph that you can see here is the number of crystalline structures that have been published in the literature in the last 50 years, okay? This is coming from a team of people from the Cambridge Crystallographic Database Center, okay? They have a curated database where they basically store every crystalline material that is included in the literature. How many MOFs do we have here? Okay, out of the 1 million structures that they reached 3 years ago, how many millions, how many structures, how many thousands of structures are metal organic frameworks? We were not the first ones to ask this question, okay? It has been different attempts. One coming from Sol and Snar is basically what they call the core MOF, okay? They were saying there are 5,000 metal organic frameworks in 2014. And we said, well, this is fine, but we always assumed that the number was going to be higher, okay? So we started working with them. We were asking these questions about how many MOFs have been synthesized, how many can be synthesized, okay, from hypothetical structures. And again, can we predict the performance, okay? Can we have a performance prediction of these materials? And do we find optimal structures for specific applications, okay? Can we really make this process fast enough? And this is a big question that we have, right? What is a MOF and what is not a MOF? So we didn't find, as I said, a proper definition apart from porous coordination networks with some potential porosity. So we started looking about what looks like a MOF and what doesn't look like a MOF, okay? We started creating different criteria criterion to be able to assign what was a metal organic framework. For example, this one is basically describing this idea that we have here. So a zinc oxygen cluster with a terephthalic organic ligand, which is basically the example of MOF5. Okay, this is the metal cluster that we have here, the organic ligand, and this gray sphere is basically the porosity of the metal organic framework. So we completed this description of metal organic frameworks, the connectivity. Okay, we started creating 7 different criteria, and with this we were able to have also different families of metal organic frameworks. Okay, and I don't want to expand too much on this, but basically we can also create different families of MOFs based on zirconium, something that is called the CPO27-like structures, zeolitic imidazolate frameworks, zinc oxide, iron MOF-like materials, copper coupled paddle wheel metal organic frameworks. Okay, different families. And at the end of the day, we were able to publish this. That was in 2017. And we were able to find how many structures can be defined as metal organic frameworks. Okay, what we found is that when we published the paper, there were 70,000, and now we have more than 100,000 different metal organic frameworks. And porous materials are about 10% of all of those. Okay, something quite interesting for me as well. We started seeing something that looks like a MOF from very, very early on. Okay, and in particular, one of the first structures, this is interesting, was from the University of Zaragoza. This is something we found, and it was published in it's difficult to find journal, but it was from the University of Zaragoza. That was an interesting one. I don't remember the people who were working on this, but that was an interesting finding. Chemical science, yeah, we published also this targeted classification of metal organic frameworks, okay, trying to assign different families of materials. And it's basically just making sure that we have a curated, I mean, basically what we communicate here is the development of a curated MOF subset, okay, working with the Crystallographic Database Center. This is the CSD, the Crystallographic Structure Database, basically being able to have a full database with porous, microporous metal organic frameworks. And now, once we have these MOFs, we can start using molecular simulations to start predicting the performance of materials, okay? We need to have some input information for the models of the molecules we want to simulate, the structures, is the crystalline structures, and then we can use different techniques. We can use Monte Carlo to answer the question, how much gas can be absorbed in one specific material? If we have a mix of gases, what is going to be the selectivity? Whereas we can use molecular dynamics to answer questions about kinetics, okay? And the output information we get is going to be absorption isotherms, diffusion coefficients, and a very detailed picture on the molecular level of the absorption process, okay? Very interesting from a fundamental point of view, an academic point of view, but it's also extremely important from the industrial application of these materials. In simulations, do they work or not, okay? This is one example. This is with a material called NU100. And all these MOFs, they have complex names, so don't worry. This is basically Northwestern University, and it's the structure number 100, okay? It's a prototypical material they define. Beautiful copper-copper paddle wheel clusters interconnected with this organic ligand that you can see here, okay? And these purple spheres are representing the different porosities that we can have in the material, okay? 1, 2, 3 different pores. And if we want to apply this material into hydrogen absorption at 77 Kelvin, this is basically representing an absorption isotherm. This is the uptake in milligrams of hydrogen per gram of material when we increase the pressure up to 100 bar. And what we have is the experimental data in black and the simulation in red. And something very important for people who are not familiar with molecular simulation is that we don't run the experiments and then we try to fit the experimental data with the simulation, okay? It's not. What we do is with the simulation, we run the simulations, we get an absorption isotherm, and then we compare this with experiment. Especially we work with experimentalists, we try to do the simulations alone, and then we send the data so they can really compare, and they can really find and realize that we are not adjusting our simulations, okay? It's just pure prediction without having any experimental data. If we can do this for one MOF, why not doing this for thousands of different structures, okay? And this is basically what is highlighted here. This is again hydrogen storage. at 240K. Okay, this is related with the Department of Energy targets. And this is the amount of grams of hydrogen per liter of material that we can really store here. Okay, basically, this is represented as a function of the void fraction, basically the porosity, okay, from 0 to 1, the porosity of the materials. And we can see 16,000 different points here coming from 16,000 different structures, okay? Huge number of data. If you try to do this experimentally, okay, it will take several lives to be able to complete all these experiments in synthesis and measurements, but we can really do this in a couple of weeks, okay? Really, really fast simulations. And we can also have a lot of different information, so we can really identify all these different structures. This basically allows us to understand physical limits for different applications. Okay, we want to have, for example, hydrogen absorption at room temperature. Does it work? Okay, we can really start doing simulations. In this case, not with hypothetical materials that were in the previous slide, but this is with real materials that have been synthesized. We can really see the evolution at different pressure. Okay, and all these different colors that you can see here is basically related with the MOV families that we were defining. So we can really find the most optimal material. Okay, the optimal material is this called BADGAM. This is the name it receives from the Cambridge Crystallographic Database Center, but this is a material developed by Professor Omar Yagi about 10 years ago. We can really understand better, okay, thinking about the percolation of the porous network. Okay, do we have three-dimensional porosity or we have one-dimensional channels? We can really find all these different properties for all these different materials. And we can also apply big data tools, okay, not only on the data visualization. So we can really start studying the different statistics for all these different materials. Okay, at 200 bar, we can really see how spread the results are. And if we work at extremely high pressures of 900 bar, for example, you can really see for this family of materials with very low capacity or much higher capacity. Whereas these zirconium MOFs, for example, in general, they perform much better than all these ones, okay? So this is something that we can always study and evaluate. Again, we can pay attention about the percolation theory, so we can really see that materials with 3D networks, for example, are going to be more interesting in general than one-dimensional channel porosities, okay? Just because in general, they are going to offer higher absorption capacities. There's a lot of information in these slides, but what I basically want to illustrate here is the fact that we can use all these different techniques to find optimal materials. And still the question I was trying to answer is, can we find a deterministic prediction for materials performance? Okay, what does it mean, deterministic prediction? It means that if we know the surface area of a material, if we know the pore volume, the pore size, the density, the composition, okay, even if it's a new structure, can I really know where is this material going to be localized? Okay, can we really map this in a landscape of properties? This is another example that we published a few years ago. Okay, that was for oxygen storage, and basically this is the capacity that we can deliver of oxygen when we store this at high pressure. This is gravimetric per unit of mass, per unit of volume. And you can say, well, the best materials are the ones with this heat of absorption. This is going to be related with the interaction of the oxygen and the MOFs. Obviously, there are some problems about these kind of statements because at this interaction, this optimal interaction, we have materials performing extremely well and materials performing really, really poorly. So what is happening here basically is it's a multidimensional problem, okay? This is why we want to have all these different descriptors to be able to map the properties of the materials, okay? And in this case, we need to know the interaction, but also the void fraction, right? We just need to find materials that are localized over here. And these are going to be the materials with a specific void fraction and a specific heat of absorption. This is complex, okay? And therefore, we always go into interactive websites. And this is something that is stored at the academic group. But as I said, this is something that we have developed together with IMMATERIAL. Okay, we have spin out this into IMMATERIAL. What you are going to see here, this is going to be the pressure, okay, for the different simulations. And this is the amount of gas stored per unit of mass. And this is the amount of gas stored per unit of volume. And every point you see here is one different metal organic framework. So you can see all the different metal organic frameworks capacities evolve when we increase the pressure. And you can see that all these orange points, the ones with low void fraction, they get stuck at low amounts, okay? Whereas all these purple materials that we had here with high void fractions, they were moving quite a lot, okay? They were very, very low at the beginning, but then as soon as we increase the pressure, we are able to move these to higher absorption capacities. Why do we want to have this flexibility here? We want to have this flexibility because basically what we want to do is to be able to select materials almost one by one, okay? Maybe this is going to be the best material, but maybe this is a non-stable structure. So from an industrial point of view, we are not interested on this one. Maybe we are interested in this one that we have here, lower absorption capacity, okay, volumetric than this one, not too much, okay, small difference, but maybe the stability or the cost of production is going to be much, much lower, okay? So we will select this. This is why we need to have all these tools. We don't like to have static data. We want to be able to go to a website like this and be able to play with all the data we have. The simulations, do they work? Okay, this is nitrogen isotherms, just to the standard technique to evaluate the porosity of the materials. And yes, it works. Simulations, because as soon as we compare with experiments, we have a very good match. And if we go for the application that we were looking here for oxygen storage, this is volumetric capacity. This is the empty tank, okay, just compressing the oxygen inside the tank. That was the best material published in the literature before this study. This is the simulations for the best material. Okay, that was a 20% improvement. And this is our experimental data. Okay, basically confirming that at high pressure, we are able to match the molecular simulation. So really, really beautiful results. Really happy with this. Still, the question is, do we really find a deterministic prediction for materials performance? Because we haven't done it yet, okay? This is just showing the Monte Carlo simulation. So what about this? Basically, as I said, what I want to have is a series of descriptors and be able to understand and predict how the material is going to work in a question of seconds, okay? And for this, we are basically talking about machine learning, and we are using neural networks for the uptake prediction, okay? What I'm going to represent here is a comparison between the Monte Carlo simulations and the machine learning capabilities that we have developed. If everything lies in this line, we will be happy, okay? This is the model training. This is something that took 3 weeks to obtain the Monte Carlo simulations for thousands of materials. And then in a question of 1 minute, we can test 1,000 structures. And you can see how close the Monte Carlo and the machine learning results are, okay? They are really, really close. They work extremely well, okay? Amazing results, really, really happy. And this is finally a deterministic prediction. But now we go to industry, okay? We want to apply all these materials, and we have another problem, which is, can we use these materials, okay? What are we going to do with a powder? And this is a key technology, again, the computational studies, but also this engineering of materials. This is something key for in material. What are we going to do with a powder? We have a powder sample. We need to pelletize this, okay? And this is a problem because if you remember, mechanical properties of the MOFs were not ideal, okay? If we compact this, we apply very high pressure, we collapse all the porosity of the materials. Whereas if we apply binders, we can block the porosity and still we will never use high pressure. So the material will have very low density, okay? You remember I was talking about the density, how important this was? This is one of the cases. Basically within material, we wanted to have this new pathway, okay, for the applicability of MOFs where we have binder-free materials, 100% MOF. We don't want to apply any pressure because we don't want to collapse the porosity. We want to be able to have the flexibility to build large structures, centimeter size pellets, mechanically robust, high per volume, surface areas, and high densities, okay? That's really, really important. And this is what I said, this is what we do in material, okay? We create these monolithic metal organic frameworks. Sometimes they are opaque, sometimes they have beautiful glassy looking, but these materials are fully crystalline and they are also highly porous and highly dense, okay? This is the comparison of a powder and the monolithic material on the gravimetric scale. So basically the nitrogen isotherm match one and the other. There is no difference between the powder and the monolithic material. The big difference is when we go to the volumetric capacity of the monolith. There is 3 or 4 times higher absorption capacity in the monolithic structure, just because in the powder we have a lot of dead volume between the particles that we cannot really use to absorb a gas. Okay, this is why we have a little bit of tail here going up. Okay, but this is something we will never exploit. And one of the first examples that we published in 2018, that was for natural gas storage. We are obviously focusing these days into hydrogen, okay? But natural gas storage was really good because there was a Department of Energy target that people said, well, with MOVs, in theory, yeah, we can reach these values, but experimentally, nobody was able to reach them, okay? That was the best experimental result that we found for a porous material, including activated carbons and metal organic frameworks. This is for a MOV called H+1, okay? And they basically took this powder that you can see here on the right, they tried to compact it with the hand, with the pressure you can apply with your hands, and that was the absorption isotherm, okay? Up to 65 bar. And this is very high, it's very far away from the Department of Energy target, but it's very, very high absorption capacity. This is taking the same powder and compacting this up to 2 tons of pressure. They are able to densify the material, and therefore the volumetric capacity increases because the density of the material is increasing as well. Okay, 2 tons is still not very high. They say, okay, let's go to 5 tons. And you see what is the problem now? The green one, when you apply 5 tons, decreases. It decreases because you start, you densify the material, but you also collapse the porosity of the material. Okay, you destroy the sample. And this is the monolithic structure, okay? Basically, a big difference between the powder and now the densified monolithic structure, okay? Much, much higher absorption capacity than any other material published so far, okay? 100% improvement versus other powder materials. And the idea behind this is basically we have some metal organic metals and organic ligands in solution. We have the synthesis of primary particles. We create what we call a wet gel. And if we have a fast drying process, okay, remember this student knocking at my door, he was putting the samples into the oven and he was getting a powder of the MOF. But when doing this slowly, okay, for example, because you forget your sample in your vents, you are able to have a very mild drying process at room temperature. And in this case, he end up with this very dense monolithic structure that you can see here on the right. Okay, big difference between this powder and this MOF. It's the same material, it's the same structure. Okay, but beautiful materials that we can really create. Just a very few slides. We can basically apply this monolithic technology to any MOF that we have been trying to work with. Okay, and we have different profiles with different micro and mesoporosity, which also means we can translate this into different performance applications, okay? And I don't want to put too much attention into these absorption capacities, but basically, if we transform gravimetric capacity into volumetric capacity of the materials, we multiply by the density of the MOFs. And then if the MOF has high density, the volumetric capacity is going to be very high. If the volumetric capacity is very low, if the density is very low, the volumetric capacity will be also very low, okay? At the end of the day, really interesting materials. We have done this for natural gas, but then we have done also for hydrogen storage. Okay, this is a paper that is ready now to be submitted. This is basically the uptake of hydrogen that we can really reach. Okay, and this is basically something that we can measure at 77 Kelvin, and the comparison with an isotherm at 107 Kelvin. Okay, if we work at cryogenic conditions, at room temperature, it doesn't work very well. But at cryogenic conditions, at 100 bar, we are able to reach a working capacity of 42 grams per liter and a total capacity of 48 grams per liter. Okay, so really, really high absorption capacities for these monolithic metal organic frameworks. Can we find a deterministic prediction for materials performance? Can we translate these predictions to real materials and applications at scale? These were the two questions that I was trying to answer. And the answer is yes. Okay, machine learning really helps us to do that. And we rely quite a lot into machine learning capabilities these days. And then we can also translate the application, the predictions that we have on performance into real applications just by working with these monolithic structures, okay, where the density of the material is finally the real density that we were predicting with all molecular simulations. A lot of different possibilities on absorption storage, for example, with hydrogen, also with carbon capture. We have also applications related with water storage for heating, ventilation, and air conditioning, catalysis. But at the end of the day, I mean, sky is the limit. There is no limitation about these metal organic frameworks, these applications in a lot of different areas. And what we really like to call these monolithic materials is these engineered porous nanomaterials, molecular response. We call them MOFs version 2.0, okay? Because the monolithic materials are really unlocking the whole potential of these MOFs. So that's the end of my presentation, and more than happy to answer any questions you may have. Thank you very much.
Thank you very much, David. I don't know if you hear me. I think it's okay. So thank you very much for the very interesting and amazing presentation. Actually, I learned a lot about that. I'm sure, more than sure, that there should be some questions in the room. I don't know if somebody wants to know further. In such case, I don't know if you can make the question directly, because we don't have the question. So, oh. I don't know if you can make the question directly, because I don't know if this is working for that. So we can do both. Maybe you can come here and make the question, or maybe you can just give me the question. I will translate it to David. What do you prefer? Because it's not, we don't have length enough. Thank you. If you get near, please. Wait, are you there?
Yes, I cannot hear anything.
I'm sorry.
I can hear you, but nobody else.
No, the audience. Oh, really?
No? Can you hear me?
Yes, a little bit.
Okay, so my question is, what is the texture of these monolithic MOFs? Because they see in kind of photos, they seem to be pretty rigid. So if you need them with a specific shape, they seem to be difficult to handle. I don't know.
I couldn't hear the beginning of the question. I mean, I hear you are talking something about monolithic materials, but I cannot hear you very well.
I think she refers to the texture. I mean, the surface area, porosity of the of the material.
Is it really rigid, or is it like a solid, or more like a gel?
She's asking if the materials are more like a gel or more like a solid. Is rigid solid, or is this a kind of soft solid?
So at the beginning, the material is the material at the beginning is a wet gel, okay, and some of these materials, they gellify during the synthesis, and we have some examples. I mean, where the material, all the solution has gellified, and we just need to extract the solvent. We need to have this mild drying process slowly. So this is wet, and this is a real gel that is dynamic. But then as soon as we have the dried material, this that looks like a glassy material, okay, this is very hard. Okay, many times we have very difficult times breaking these particles if we want to make some characterization. So this example you have here at the bottom, this is a very rigid and hard sample. You can see this bright on this particle, for example, here. Okay, this is just the light getting reflected. This is this glassy look that we like to get when we have monolithic materials. But these are very rigid, very hard samples.
She says thank you. Oh, interesting. So, so there is any other question, comment, ideas? I think it's a little bit uncomfortable to make questions, but we can just make some other. Well, meanwhile, the people thinks in the next question. I have also referred to this. I don't know. Yeah, I think you can hear me. Refer to this specific slide you're showing now. in the case of this rigid, this softness, this material is the transparency is due to because the density of the material is really low, I guess.
The packing of the material.
Packing. So the packing is really very open, no? So
so if we really look and we compare, okay, let's compare this. Okay, so here you have in the powder, you have all the light scattering on the surface of the material. Okay, on the external surface of every crystallite that you're having. Okay, so it's a lot of light scattering, and this is why it looks white. And the big difference, okay, is that in this material, we must have a really good packing of all these primary particles that we are having in our material, okay? And this is common for any material. If you have something which is transparent, it means that the size of the objects that you have is probably going to be about 40, 50 nanometers, okay? And also there will be no contrast in electron density with the different phases that you're having, okay? If you have big mesoporosity, I think I have, here, this is a very good example. You see the difference between this material, which is and these ones that are more glassy, okay? This one is the red one, okay? The blue and the red one are these ones that have mesoporosity, okay? Whereas the ones that look more glassy, more transparent, are the ones with lower mesoporosity. And this is because we have a lot of space between the crystallites, okay? And this is where the light can have some scattering.
I see.
In the case of the highly dense materials, these are very packed, and the light doesn't have, I mean, there's no scattering, okay? A very good way of studying all these materials as well is not only with gas absorption, it's also with small angle X-ray scattering, and it's basically doing the same. Try to characterize the scattering of the light, in this case, X-rays, when we heat these materials, okay? And just with this, we can really know what is the size of the primary particles, what is the packing, morphology, and so on.
So, and this is mainly due because of the evaporation. You have the soft gel you have at the beginning, and then the slide you have over there. You have a mild rain, which is a kind of evaporation, very soft evaporation of the solvent. And then at the end, you get all the molecules arranged in a dense monolith.
Yep.
So all the liquid is spelled out of the gel structure.
Yeah.
Finally, you have a dense monolith. Oh, interesting.
Yeah. In this case, when you have a fast drying, okay, you disrupt all this gel that you were having here, and you just have the primary particles isolated. Okay, sometimes you have some agglomeration, but at the end, you end up with this powder. The big difference, I mean, this is really coming from all the sol gel science that exists. Okay, I mean, this is thousands of papers about talking about these kind of ideas. And I mean, in particular, I was working, even during my PhD, with carbon aerogels. So I was working on monolithic materials, but they were based on organic resorcinol formaldehyde gels. And then we were producing activated carbons out of them. And that was the big thing. That was the big opportunity, because we were having the same idea of creating primary particles, then having a gel process, and then being able to have, in our case, to create an aerogel, you need to have a supercritical drying process to be able to not disrupt the porous network that was created in the gel. But in our case, what I think is we are also combining all these sol gel processes with an extended reaction, extended synthesis of the material. Okay, and basically the reaction, the synthesis reaction continues a little bit, and then we create these dense monolith samples here.
So the last step is not real. The drying step is like a drying and reaction step at the same time.
It could be. It could be.
Okay. Where the not only the clusters, but also the molecular linkers, the organic linkers are still reacting and forming denser structures. No?
Yeah, exactly. I mean, so this is one of the assumptions that we have. Yeah.
Okay. So thank you very much. Questions? No? Let's see if somebody in the, because we have a chat. There is no questions, by the way. So I will do another question, because really, I was really amazed. It's just not In terms of catalysis, application of these materials in catalysis, because for gas absorption, I think is of course, it's a very interesting material, very good material for absorb gases at different pressures, even at very high pressures, even at 300 bars. Sorry. But in terms of catalysis, applications in some reactions in which the temperature is a key factor, what do you expect about this material? What do you expect about the performance of this material?
MOFs, they should not substitute zeolites. Okay, so a zeolite is a very good material where you can really work at very high temperatures. What we are really aiming here is to be able to have catalytic reactions, for example, that can work at much lower temperatures and milder conditions. A MOF, I mean, some MOFs are stable at relatively high temperatures of 200 or even 300 degrees, but I will be a little bit cautious about these fields. Okay, we have been using in some applications MOFs catalytic reactions at room temperature. Okay, and they work really well. So, for example, with the degradation of nerve agents, and this is working, as I said, at room temperature. And zeolites will have some problems because the porosity is not big enough for these big molecules. So this is the opportunity with these materials. Okay, it's not to substitute excellent catalytic materials like zeolites, but to really try to find new opportunities where zeolites they don't work.
Okay. I think we have a questions in the
yes, hello.
Yes, so please.
Hello. Thank you, David, for your very nice talk. I really like a lot. I miss a short part because, as you see, I'm in a lab coat. So I'm in the lab actually working with MOFs. So we are very interested in that. And in particular, also about your talk about the degradation of nerve agents. We are also working in that field, degradation and also the sensing of these nerve agents. And as far as I'm concerned, the publications about degradation of nerve agents, usually they are in liquid phase, they're in specific conditions, they maintain basic media to avoid any deactivation also of the catalyst because you create the acid. Could you comment on this? What is your experience in this degradation of nerve agents?
So most of the times when we try to work on this application, we don't try to do this at home for obvious reasons.
Sure.
We send this to big experts that they really know how to handle these gases and these compounds, because obviously we will have a lot of problems. We have been working with some simulants in the past a little bit on the gas phase, okay, and making sure that we have, I mean, it's basically a breakthrough experiment where we have our material and we just flow the gases, and we either see if we are able to capture the gases, the components that we want to remove, or if we are able to degrade them, okay, and I mean, at the end of the day, the Department of Defense, we work with the Department of Defense in the UK and the US, and they basically have some kind of very well-established protocols. And they just, if they are using an activated carbon, they are using a MOF, they use all these materials on the same way. The best material for nerve agent degradation, catalytic degradation, is something called MOF 808, but this is something that is very well described in the literature.
Yeah. Sure.
The challenge for us is really being able to create monolithic materials out of them.
Okay, thank you. So you are working on the creation of these monolithic materials out of 808. Okay, yeah, that's true. You can work with the simulants, but the real conditions, and not only thinking of the real nerve agents, but also in the real condition when you have the release. Creating an experiment for capture is clear, make a breakthrough curve, but the concentrations and so on, that's also challenging.
In our case, we always give the samples to these people, and they have the very well established protocols.
I can imagine who. Peterson and so on.
Because, for example, also stability of the materials, okay? Water stability with moisture. They cycle the materials 100 times, for example, with high levels of moisture, high temperature, they go up, down, so the water is going out and inside of the material, and really making sure that the material is stable.
Okay. Thank you, David.
Thank you, Ray. Thank you very much. Any other question? No, so far. Just one question I just mentioned about the stability of the material, because okay, MOFs are not the most stable material in the world, of course, but very stable enough to stand for some pressure or some conditions. But how about the capacity of this material to be recycled? I mean, you just put some gas inside, take the gas out, and then do it again. There is some problems in the structure when they happens very many times. I mean, which is the capacity of the material to be recycled?
I think, yeah, I mean, this is one of the key ideas that we want to have, right? We need to ensure that these materials are stable when exposed to moisture, but also we want to cycle these materials and make sure that they are really, really stable. Some of these materials, we have done this for water absorption, okay? And again, we send this to some of the clients we work with, and they do the testing where they have 100 cycles with the material for water absorption. And again, they make sure that the material is not losing any capacity on the process. So this is where we said, okay, we are really confident this is working properly.
It looks like very interesting. So thank you very much, David, again. I think there is no other question. So let's thank again David for his amazing and interesting presentation. And hopefully we can see you again soon. Okay. So thank you very much.
Thank you very much for the invitation.
Thank you.
Welcome.
Sure, we can collaborate. I'll talk to you later.
Hopefully we can collaborate. Okay.
Okay. Gracias, David.
Muchas gracias.
Gracias a vosotros.
Hasta luego.
Hasta luego.
Sí.
Hasta luego, David.
Hasta luego, David.
Hasta luego.
Estamos en contacto.